Hi everyone, my project this summer was on laser beam wave acceleration in a dense magnetized plasma. So first, a quick introduction on laser wave field acceleration. So laser wave field acceleration is a process where we can excite plasma waves using a laser pulse through the stimulated Raman scattering effects. So if we have an incident laser that oscillates at frequency omega naught, then it will travel through the plasma and it will scatter off the particles in the plasma and excite plasma waves that oscillate at the plasma frequency omega p. Yeah. So from Planck, we know that an electromagnetic wave's energy is proportional to its frequency. So conservation of energy tells us that omega naught is going to be equal to omega p is going to be equal to omega naught minus omega 1, where omega 1 is going to be the frequency of the scattered wave. So similarly, we can also excite plasma waves using the beats of two lasers. We're going to follow the same energy conservation equation, but now omega 1 is going to be the frequency of the second incident laser. So here's a little visualization of what's going on. So we have a little laser pulse that's going to perturb the electrons from their equilibrium position. They're going to oscillate around that position. They're going to create cavities of charge imbalance, and that's going to create longitudinal electric fields in these cavities. So that allows us to accelerate charged particles in the direction of propagation of the laser. So a laser can be, a plasma can be thought as a fluid. So we can make an analogy with ducks in water. So if we think of the laser as a mama duck, then as she travels through the water, she's going to create wakes. Those wakes can then be ridden by her little ducklings, which are going to be our little charged particles here. So that helps them move around along the water and helps them save energy. So why does this matter? So, I mean, I already said that we have a longitudinal electric field. We can accelerate charged particles, and that obviously has applications to experimental particle physics and also medicine. So, the phase velocity of the plasma waves is going to be equal to the group velocity of the driving pulse because relativity. So that group velocity is going to decrease with increasing plasma density. So that means that as we increase the plasma density up to near critical density, which is given by this equation, critical density is also the density for which at a certain frequency, the plasma becomes a perfect reflector. The phase velocity of the plasma is going to decrease, and then the intensity of the electric field is going to increase. So this is a quick plot of a laser beat wave acceleration experiment done at near critical density. So here we can see that the magnitude of the electric field is 10 to the 11 volts per meter, which for quick context, in traditional particle accelerators, this is going to be 10 to the 6 volts per meter. So this is about 100,000 times greater than those traditional particle accelerators. So why does the lower phase velocity matter? Well, for the electrons to be trapped and then continuously accelerated, we need for them to be in phase with the plasma wave. So that means that they have to have speeds comparable to that plasma wave. So we want a plasma wave that has a phase velocity that's going to be able to trap a significant number of electrons either near the tail end of the particle distribution or at the bulk. So if we assume thermoequilibrium, then our electrons are going to be described by a Maximilian distribution. So what this is saying is that we want the laser pulse to either have a phase velocity around here to trap particles here, or ideally near the bulk. So where does my work come in? So if we add a magnetic field in the direction of laser propagation, then the dispersion relation for a left-handed circularly polarized wave is going to become this shown here, where omega c is the cyclotron frequency. And here we can see a little plots of that. The L wave dispersion is right here. And we can see that it actually intersects the plasma frequency. So that brings the question, can we excite plasma waves directly by using lasers that oscillate at the plasma frequency? Also, we can see in the equation that the only thing that we can vary is going to be the wave number, K, and also the magnetic field. So that also brings another question. Can we use the magnetic field to control the plasma wave number? This is similar to saying, can we use the magnetic field to control the phase velocity, since the phase velocity of a wave is just omega divided by K. One thing to note, the wave number of the plasma wave is going to be given by conservation of momentum, given by this equation here. So how do we go about this? We use the particle and cell code Smiley to conduct 1D simulations of a 10 eV plasma. We use absorbing magnetic conditions on the Nernst Bermuda HPC cluster. We also used a plasma density of 10 to the 21 particles per centimeter cubed. And then we changed the magnetic field strength and the laser frequency. So this is some initial results. This is a magnetic field of 25 Tesla. We use an intensity, laser intensity of A naught equals 0.1, where A naught is the normalized vector potential. The frequency of a laser here is the plasma frequency and has a pulse width of 1 picosecond. So this is an initial time shots of when the laser first penetrating the plasma. So here we can see how the laser goes from the vacuum dispersion to the plasma dispersion. And then at a later time, we can see the development of a soliton-like wave in the actual plasma. So the red line is the laser transfer field. The blue line is the actual longitudinal field in the plasma. And we can see that that longitudinal wave does seem to follow the dispersion relation given by the electric wave in the plasma.
What are the axes on this graphs?
So this is space. So we have a plasma that's 40 microns thick. It's going to go from 10 microns to 50 microns. So this is the plasma here. And then this is the magnitude of the electric field. And then this is a one-dimensional FFT over space. So here we have the wave numbers. Here's the time evolution of the simulation. So this line here is the wave number we expect from the dispersion relation. We do see that there is some excitation here, but that most of it is a little bit past it. Part of this could be because this is a low frequency FFT. I would have to redo the runs for to get better resolution. Another issue is also that this is expecting that the frequency of the laser is greater than the plasma frequency. This is at the plasma frequency, so new physics come into play here. We also have B wave simulations. So now the lower frequency, the seed frequency, is going to be a little bit greater than the plasma frequency. Here we see a later time shot of this simulation. We do see high amplitude electric fields on the order of 10 to the 11. It's a little small, my bad. And then we also have FFTs of the transverse field and the longitudinal field. So these here are the fields in vacuum where we would expect them. This is the fields in the plasma, again, where we expect them. The only thing we change here as well is that the laser intensity is a little lower. A naught is about 0.01. And then here we see the EX field. The wave number is where we'd expect it from conservation of momentum. And now this is a plot where the laser frequency is the plasma frequency. So here again, we see the same high magnitude electric fields. The wave numbers are where we would expect them. Same here. One thing to note though is that we see the development of a large sheath field right here. So this tells us that the plasma is non-neutral. So it does suggest that we have accelerated a significant number of particles from the plasma and they have left it. So that's exciting. And then lastly, we have two-dimensional FFTs. This is just the dispersion relation of lights in a vacuum. We see some signals here as we would expect them from the laser. And then again, for the EX field, we see a large excitation at the plasma frequency, at the frequency, at the wave number we also expect. So my work only analyzed the fields. So something that could be done immediately after this is seeing how many particles were actually accelerated into what energies. Additionally, you might also want to investigate how the problem changes in higher dimensions, like 2D, 3D, see if anything else changes in that regime. Yeah, and then thank you for your attention. I'd like to thank my mentors and then references as well. Any questions?